Hello everyone, welcome to my Data Camp tutorial series. I'm Professor Adam Kroom, and today we will focus on AI Fundamentals Chapter 3, Unsupervised Learning. Go ahead and hit Continue Chapter, and it will take you to the first video, Dimensionality Reduction. Go ahead and watch the video, Dimensionality Reduction. It will give you important information on how to solve the exercises in this chapter. And after you've watched the video, click Next Exercise. It'll take you to the first exercise, Principal Component Analysis. To which family of dimensionality reduction algorithms does principal component analysis belong? Possible answers are: principal component analysis is an example of linear dimensionality reduction algorithm, or principal component analysis is an example of nonlinear dimensionality reduction algorithm. And I'm going to go with the first one. Correct. Being a linear, fast, and deterministic algorithm makes PCA the first choice to test when going with dimensionality reduction. Press enter to continue. The next exercise is called Visitors from Outer Space. So you concluded you must resort to dimensionality reduction because of very limited computational resources you have available for crunching your hyperdimensional dataset. And for the same reason, you feel that the PCA algorithm is the best choice due to its speed and simplicity. Good, but did you check your data for outliers? Let's see how they could impact your results. A three-dimensional data set of 1,000 samples, slightly contaminated by 5 outliers, has been preloaded as seen on figure 1. And the 1,000 samples are x underscore raw, and the outliers x underscore new. On figure 2, you see that the impact of these outliers in red is trivial and creates no problem in extracting actual principal components. But what happens if they are further away? Instructions. So we have two parts to our instructions. The first part says add 5 outliers with an outlier distance of 200. So looking on the right, it says add outliers to the blob. So the first thing we need to fill in here is outlier underscore distance equals 2. And it tells us right here, outlier underscore distance of 200. So type in 200 right there. And n underscore outliers, and it tells us right here, add 5 outliers. So right here for n underscore outliers equals 2, we'll set that to 5. And let's submit an answer. All right, so now we're on to part 2 of our instructions. And part 2 of our instructions tell us to extract the first 2 principal components of the contaminated data set, x underscore new, using the helper function, extract underscore components. Okay, so looking over on the right, it says extract principal components. And n underscore components equals 2. We're going to set that equal to 2. And let's submit our answer. Correct answer. But that doesn't seem right, does it? The first principal component is now completely skewed towards the outliers. But how can 5 outliers outweigh 1,000 normal samples? The problem is in the magnitude of these outliers, which dwarfs the variations observed in normal samples. Key takeaway: before any dimensionality reduction, always make sure to properly explore your data and treat outliers if needed. And press enter to continue. So we have our next video here called clustering. Watch the video on clustering so that way you know how to solve the next exercises. And after you've watched the video, Hit next exercise, and it'll take you to this exercise called Lucky Number K. Beginners in machine learning often have very optimistic ideas that machine learning can produce amazing insights with little to no human involvement and decision making. The truth is that the performance of your algorithm is heavily influenced by parameters that you as a human define before the model has seen any data. In the case of clustering, most algorithms still require you to be explicit about the number of clusters you are looking for, but not all. Which of the following clustering algorithms determines the number of clusters on its own? And our possible answers are k-means clustering determines the number of clusters on its own, spectral clustering determines the number of clusters on its own, or dbScan determines the number of clusters on its own. And I'm going to go with dbScan. That's it. dbScan determines the number of clusters on its own, but that doesn't mean that the discovered clusters will always be meaningful. Make sure to always inspect the results and adjust algorithm hyperparameters if needed. Press enter to continue. The next exercise is called elbow reading. Determining the right number of clusters is one of the most crucial steps in developing a clustering model. In this exercise, you will apply k-means clustering and the elbow method to determine the correct number of clusters present in the data set at hand. The data is loaded in the variable x, and you have been provided with two functions for your convenience, plot underscore clusters and plot underscore elbow underscore curve to facilitate the discovery process. Your task is to specify the range of numbers of clusters over which to scan in order to produce the elbow curve. We got two parts to our instructions. The first part is set the values of start and stop parameters of the range function in the first line to 2 and 6 respectively. So looking over on the right, it says k underscore range equal to list range. And then right here, we'll plug in 2. And in the second position, we'll plug in 6. Right? It tells us right there. Um, uh, First line to 2 and 6 respectively. So we just did that. And let's submit answer. All right. Now we have part 2 to our instructions. And it says, according to the shown curve and scatter plot, what is the most reasonable number of clusters in the data set? So our possible answers are 3, 4, and 5. And I'll give you a moment to look. And I'm going to go with 4. That's correct. The sum of square distances stops dropping significantly for values of k above 4. Press enter to continue. The next exercise is called dbScan. dbScan is another very popular clustering algorithm belonging to density-based algorithms. For beginners, it can seem very attractive because it doesn't require the number of clusters to be defined in advance. But there's no free lunch, and relying on dbScan to find the right number of clusters completely on its own can be a big trap. Let's illustrate this by playing with dbScan's hyperparameter EPS, which defines the maximum distance between points within the same cluster. So we have 3 parts to our instructions here. The first part says set the value of EPS to 0.1 and check the clustering result. All right, so if you look on the right, it says set EPS to 0.1, EPS equal to 0.1. Genius, right? Submit answer. All right. Next, for part 2 of our instructions is, it says setting the maximum distance to 0.1 did not yield any clusters. Try setting the value of EPS to 0.5 and check the clustering result again. Okay, so over here on the right, it says set EPS to 0.5. So EPS equal to 0.5 and submit answer. Cool. So we're on part 3 of our instructions, which says you found 3 clusters. However, there are still a lot of points that don't belong to any cluster. Set the value of EPS to 2 and see what happens. All right, so go over to the right and it says set EPS to 2, EPS equal 2, and just type 2 and submit answer. Super easy. Increasing EPS to 2 did cluster more points, but it also merged 2 clusters together. None of the options you tried seems close to acceptable, right? dbScan is a density-based algorithm and as such might be completely inappropriate for certain data sets because it tends to merge clusters with overlapping regions. Choose your algorithm wisely and always try multiple options. Press enter to continue. All right, so we're at the next video called Anomaly Detection. Watch the video and it'll teach you useful information about anomaly detection for the next exercises. And after you've watched the video, click next exercise and it'll take you to this exercise called How Unsupervised Really. When evaluating the performance of anomaly detection models, you most often use metrics from the domain of, and our possible answers are supervised learning or unsupervised learning. And let's go with supervised learning. Correct. Just because you don't have enough labeled data to apply supervised learning doesn't mean that you shouldn't use any amount available to test the performance of your model. Press enter to continue. The next exercise is called the go-to algorithm. Despite being a bit more computationally intensive than other methods, an algorithm is commonly used for anomaly detection. Which algorithm is it? Our possible answers are one class SVM is commonly used for anomaly detection, isolation forest is commonly used for anomaly detection, or robust covariance is commonly used for anomaly detection. And I'm going to go with isolation forest is commonly used for anomaly detection. Submit the answer, and that is correct. For most applications, and given the general availability of computational power today, isolation forests are the go-to algorithm for anomaly detection. Press enter to continue. We're at the next exercise called the odd one out. You saw previously that the isolation forest algorithm is a great first choice when in need of anomaly or outlier detection. In this exercise, you want to examine how the ratio of inliers to outliers, aka signal to noise ratio, affects its ability to detect anomalies. The isolation forest algorithm has been loaded for you in the variable called isolation underscore forest. And a helper function, make underscore fake underscore data, was loaded as well. Your task is to gradually increase the number of outliers and observe the difference in results in each iteration. So we have 3 parts to our instructions. The first part says set the number of outliers to 50, 5% of inliers. So looking over on the right, it says generate data comprising of the clean and noisy components. And here we have to fill in something. N underscore outliers equals 2. Well, it tells us right over here. In the instructions, set the number of outliers to 50. So I just typed in 50 right there. And that's the only thing we have to fill in for part 1 of the instructions. Submit your answer. And that is correct. So part 2 of our instructions, it says set the number of outliers to 200. 20% of inliers. All right, so here it says on the right, generate data comprising of the clean and noisy components. And we have to fill in something for n underscore outliers equals 2. And over here, it tells us to set it to 200. So we just type 200 and submit answer. Cool. That is correct. And now we're on to part 3 of our instructions, which is to set the number of outliers to 500. So easy work, right? You just come over to the right. It says n underscore outliers equal 2. There's a blank spot right there. Right there, you just want to plug in 500. And that number comes from right here. And submit answer. Good. Although you clearly see that isolation forests, even without any tuning, do an amazing job of detecting anomalies, they cannot do miracles if your data is severely contaminated. It's good to remember that in that case, they will tend to overestimate the number of anomalies, raising a lot of false alarms. Press enter to continue. The next exercise is called Elon's tweets. In this exercise, you will attempt the impossible, detecting patterns in Elon Musk's tweets. You will apply 2 unsupervised learning algorithms, dimensionality reduction to translate your text data into a 2D space, and clustering to find groups of similar tweets. The go-to model for dimensionality reduction is principal component analysis, while the k-means algorithm represents the same in the domain of clustering. Tweets in their raw form were loaded into the variable named tweets underscore raw. They have also been translated into a machine digestible vectorized form contained in the variable tweets underscore matrix. To write less code, we want you to use the functions for combined fitting and transformation prediction, dot fit underscore transform and dot fit underscore predict. Instructions. Set the algorithm for dimensionality reduction and the number of dimensions to 2. Apply dimensionality reduction to the vectorized dataset tweets underscore matrix. Configure the clustering model to find 2 clusters in the input data and find clusters within the reduced dataset and display the results. The latter step has already been done for you. All right, so looking over on the right, it says set the number of dimensions to 2. So over here for n underscore components equals 2, we're just going to type 2 right there. And then next it says apply dimensionality reduction. So to do that, right here we have dimensionality underscore reducer dot, and then we have a blank. So in this blank spot, we're going to type fit, fit underscore transform. Reducer dot fit underscore transform. And then in here, we're going to type tweets underscore matrix. All right. So let's see, dimensionality underscore reducer dot fit underscore transform. Cool. And then next it says configure the clustering model. So here k means n underscore clusters equals to 2. And then next it says find clusters. So here we have clustering underscore model dot, and then it says, we're going to do fit underscore predict, and then tweets underscore reduced. And then show the clustering results. And that's already been done for us. Cool. So let's submit our answer. Fantastic. Clustering helps you find patterns in the data, but the result is strongly influenced with how the data was prepared before being served to the learning algorithm, as well as your choice of the number of clusters you are looking for. Here you can see 3 groups of points with your eyes, but you have asked the algorithm to split the points into 2 clusters, and that's what it did. It is a very rough divide, and it looks like the algorithm has mainly put all retweets into one bucket and all other tweets in the second one. Press enter to continue. All right, and then we're at our next video called Selecting the Right Model. Go ahead and watch the video, and after you've completed the video, hit next exercise, which will take you to this exercise called Fruits of Knowledge. When you want to know why your model has made a certain decision for a specific single record, you are engaging in so-called local model interpretation. Currently, the most popular algorithm for this purpose has a very fruity acronym. Which one is it? And our possible answers are lemon, lime, orange, and papaya. Let's go with lime. Yes, LIME stands for Local Interpretable Model Agnostic Explanations. Although it's a fairly recent algorithm, it already has implementations in several machine learning libraries in Python, such as Eli 5. Press enter to continue. The next exercise is called Predicting Customer Churn. Congratulations, you have just been hired as a junior data scientist for a big telecommunications company. On your first day, you're asked to help with a big problem the company is struggling with, predicting customer churn. Luckily for you, your colleague has already prepared the data set for you. You just need to use it to train a predictive model and determine its performance. The exercise data sets have been loaded for your convenience. Client underscore data holds the inputs: gender, tenure, monthly costs, number of dependents, and so on. And client underscore churned holds information on whether this client churned or not, yes or no. As for the models, you have the random forest classifier and linear regression at your disposal. Choose wisely. Instructions: select your model, split the preloaded client data into the training and testing set using the train underscore test underscore split function, train the model, and generate predictions on the test set and evaluate model performance using accuracy, precision, and recall as metrics. Okay, so looking on the right, it says define your model. Model equal to, I'm going to use random forest classifier. Divide the data set into the training and testing set and train the model. So to do that, y test equals 2 train underscore test underscore split. And then here, first argument, client underscore data. And secondly, client underscore churned. And then model dot fit. Okay, and then next it says generate predictions on the test set. So here we have predictions underscore test equals to model dot predict x underscore test. And then finally it says evaluate the model predictions using metrics appropriate for this problem class. So here we have 3 blanks we have to fill in, and it tells us right here, right? How convenient, right? Accuracy. So I'll just go ahead and copy and paste. And then we have precision. So I'll copy and paste that. And then finally we have recall. So I'll copy that here and paste it over here. And then submit answer. Good job, but what does this mean? When your model flags a client as a churner, it is correct in 67% of cases, precision, and you're able to detect 43% of the churners, recall. These are not the same thing, and it's very important to understand the difference. All in all, not a great performance, but not a bad one either. In any case, you now understand the core end-to-end flow of building supervised learning algorithms. Press enter to continue. Good job. You have completed chapter 3, unsupervised learning. Thank you for your attention. I will go ahead and film a distinct video for the last chapter, chapter 4, deep learning and beyond.